All right, so we left off here last time. My announcements for today / the week. There is mastering due tonight, which you should be able to, about half you guys have completed it, so that's good. And there's also mastering due Friday night. There'll be a group quiz on Friday, and your first individual quiz will be on Monday. Good? Good?
Will our individual quiz cover like everything he's done, or just
Technically, everything's fair game for every quiz.
Okay.
But typically it's just the most recent stuff. So. All right, in that case, now that we have discovered atomic theory in John Dalton's four-part atomic theory, we can talk about what is an atom. All right, so the atom is the basic unit of an element that can enter into a chemical combination to make a new compound. And atoms contain three main parts. They have an electron, a proton, and a neutron. All right, the electron is the negatively charged portion. The proton is the positively charged portion. And the neutron is considered neutral. Right, and all atoms are going to contain those three particles in some combination. So what we're going to do is we're going to look at each of these parts individually and then recombine them to see how we end up with the current model of the atom. So a little bit of walking down chemistry history lane for the next few slides. So in 1897, so not that long ago, right? A little 110-ish years ago. They found the first evidence for subatomic particles when they passed electricity through gases. So J.J. Thomson in 1997 did this experiment, which I'll do these both at the same time. It is the cathode ray. And what he did is he designed this experiment where this tube contains gas, and he would send negatively charged particles. He didn't call them electrons at the time. So negatively charged particles would pass from this end to that end. And then what he did is he turned on this electric field across the top and bottom, and he saw the negatively charged particles, these guys, would all of a sudden start scooting up towards the top. So that was his evidence that there were negatively charged particles. And these negatively charged particles he started to call electrons. Let's see. The other thing he determined was that the electrons have a mass much smaller than an atom. Which would mean, right, the electrons are part of the atom if they're smaller than the whole thing. And in fact, they're about 1/2000th of the mass of an atom. Once they figured out that there was such thing as an electron, the next thing they wanted to know was this exact mass. Besides being ballpark 1/2000ths, the next thing was the milk and oil drop experiment. which was done about the same time, early 1900s. In this particular experiment, they would send oil particles and send them through a positively charged plate, which would give them a charge. And the particles would then, some of them would be pushed down towards the negative and some of them would be pulled up towards the positive. And as the oil droplets fell, at some point, they'd levitate, right? So they get caught in between the positive and negatively charged plates. And based on how far down they went before they kind of got suspended in midair, they were able to back calculate how much mass that was, knowing this, size and gravity effects. So the milk and oil drop experiment proved that electrons had mass. And the mass was determined to be 9.10 times 10 to the negative 28 grams. Pretty small, right? Because that'd be 0.28 zeros and then 9. So really, really, really small mass. All right, so now it's early 1900s. We know we have electrons in there. They know they have some sort of mass. So now the scientists at the time are trying to figure out how do we put together all the things we know about the atom in terms of charge and what's part of it. Because they knew that an average atom, if you took an atom of iron, it had no charge. Well, it definitely has a negative thing in it, right? They just show the electrons are there. There must be some sort of positive particle in there to make the charge all balance out. So since the overall molecule, or atom, is neutral, they have electrons, therefore there must be some sort of positive particle. So they had this early model of what they thought the atom may look like. And the first one was called the Thomson model, after Thomson, in the early 1900s. And it was either, depending on who you are reading, I think our textbook calls it the blueberry muffin model, but because Thomson was British, he called it the plum pudding model. Same idea, that the atom has a shape, and the electrons are just in there willy-nilly, and the positive parts are in there, and so it would look like a blueberry muffin. Doesn't that look like a blueberry muffin? Maybe, maybe. Where the electrons are the blueberries, and then the rest of the atom shape is just positive in general, just a big old shape with some negative bits in it. This, So the Thomson model is this either blueberry muffin or the plum pudding model. So that was the model at the time. So about 1909, 1910, Rutherford set out to determine, I guess 1911, determine if that was in fact the correct shape. So what Rutherford did is he took this piece of gold foil and he used alpha particles, where alpha particles are positively charged particles. And if, in fact, we had the blueberry muffin model, right, which was this, something like that. Now, he would expect these positively charged molecules, positively charged particles, just kind of zip right through. You know, because the electrons aren't really in the way. Such a big space and just little tiny negative spheres that if the Thomson model was correct, it would just zip right on through. That's not what he saw, which is why we don't use the Thomson model anymore. Everybody may jump to that conclusion. Not what he saw. Instead, most of the alpha particles went through. But some of them bounced back. The only reason they would bounce back means they must have hit something, right? They must have hit something hard enough to cause it to reverse directions. And so Rutherford determined that this is my beam of alpha particles, right? This one zips through, that one zips through. This one comes back, this one gets deflected, this one comes straight back, which means there must be a hard center to an atom. Has a hard, well-defined center. Which is how we have the model that we have now, right? We don't assume that the electrons are just everywhere in this open range. When we draw an atom, we have it with a well-defined center. And the electrons are scattered around the outside. So our current atomic model looks like this. 1, most of the atom's mass and all of its positive charge, that should be core, sorry, in a small core that we call the nucleus. Most of the volume of an atom is empty space, and that's where the electrons live. And 3, there are as many electrons as there are protons. Right, and that's what makes the overall atom neutral. If you have as many electrons as protons, where the electrons are the negative thing, protons are the positive thing, you have to have an even number, otherwise they won't balance out. So now, when we think about drawing an atom, right, you typically draw something that's a big circle with a little tiny center, and the center is where the positive charge is. Something like this. Let's go this way, if you're still writing. Right, so here is my gigantic atom, not life-sized. I am so much smaller than this. All right, so here's my atom. In the tiny hard center, we have protons and neutrons. I'll talk about neutrons here in a second. On the outside, right, we have the electrons just floating around. If I just draw 7 electrons, how many protons should there also have to be? Right, so there's going to be 7 of these. Good. All right, so if you think about how big an atom is, the whole atom is about 100 picometers. Right, so 1 times 10 to the negative 10th meters. The size of this nucleus is 5 times 10 to the negative third picometers, which would be 5 times 10 to the negative fifth meters, or 0.005 picometers. So that's hard to imagine. So think about your football stadium, right? Regular old high school football stadium. Put a marble on the 50-yard line. That's how big the nucleus is compared to the football stadium. So the football stadium is the whole volume of the atom, and where all the positive charges is in a marble in the center of the 50-yard line. So pretty dramatically different, right? So let's talk about what makes those protons and neutrons so important to how an atom works. All right, let's see. Do I have something else? Let me tell you some fun facts first before I get ahead of myself. Oh, just kidding. Electron. All right, so far we have the proton and the electron, which that's the positive guy, that's the negative guy. If we just look at the protons and electrons in an atom, it was shown that the mass of a single atom didn't add up correctly. Right, so they had this electron, they had the proton. Electrons had pretty much no mass, nothing. Protons, they definitely showed had some mass, but when they weighed a single atom of like boron, it didn't come out correctly. So there must be this other particle in there. So if I look at, we'll do helium. All right, so helium has a mass of 4 atomic mass units. When they did some experiments, they figured that it had 2 protons and 2 electrons. But the electrons don't count. And if every proton is worth 1 atomic mass unit, they are missing some weight. All right, so if 1 proton is 1 atomic mass unit, they have only weighed out 2, but they know it weighs 4. So how much mass are they missing? 2. Can the 2 AMUs they're missing have a charge? No, right? Because we already accounted for charge. We got 2 protons, 2 electrons. Well, if I made it 4 protons, 2 electrons, that'll take care of the mass. What have I just done wrong? Right, now it's going to be positively charged. That's no good. So there must be a particle that has mass equal to 1 atomic mass unit, but 0 charge. So what do we call that guy that has mass equal to a proton but no charge? We got the neutron. All right, so now we have our 3 particles. We know that there's a proton, an electron, and a neutron. So now we're ready to kind of put them all together and figure out what makes an atom of one thing different than an atom of another thing. It's going to have something to do with what we just talked about. Everyone caught up on that? Yeah. All right, so let's talk about protons, neutrons, and electrons, atomic mass units, charges, atoms, ions, isotopes. All right, so by definition, an atomic mass unit is 1/12 the mass of a single carbon atom that contains 6 protons and 6 neutrons. So if I know that a proton is equal to a neutron in terms of mass, I have 12 mass things, right? So if I have 6 protons, 6 neutrons altogether, I have 12 AMUs, which means each proton's worth 1 AMU, which you guys probably already knew already, but I thought I'd cover it again. So if I have one atom of carbon that has a mass of 12 AMU, right, because it has 6 protons, 6 electrons, which if you can see the periodic table from where you're sitting, it is this number on the bottom, right, that 12.001, that is the atomic mass units for a given atom. If I look at, bless you. I'll go to oxygen, which is right over here. The oxygen, if I look down, it has a mass of, we're just going to call it 16 for simplicity's sake, 16 atomic mass units. So what does that tell you about the number of protons and neutrons in oxygen compared to carbon? Who has more protons and neutrons? Right, oxygen should have more protons and neutrons. Good, good, good. All right, so since the protons and neutrons have electrical charge, but the overall atoms are neutral, the atom must contain equal number of protons and electrons, with the mass being determined by number of protons and neutrons. So this will help us figure out how many of everybody's in there. So everybody's neutral for now, which means protons and electrons are equal. But if I know the mass tells me number of protons and neutrons. So we have 2 equations and 2 unknowns most of the time. So we can figure out the number of everything. So let's look at some elements in particular. So what makes an element unique is the number of protons, neutrons, and electrons it contains. But what identifies an element is the number of protons. So elements are each different from each other, that they have a different combination of protons, neutrons, and electrons, but we classify elements based solely on the number of protons that they contain. So let's say we'll go back to good old oxygen. All right, so if I'm looking at oxygen, it's atomic number 8, right? It's the only 8 on the table. That 8 tells me there are 8 protons in it. There's no other element that has 8 protons. Or I can look at zinc, right? Zinc tells me number 30. So it tells me it's the only element out there that has 30 protons. There's no way, if it had 31 protons, it wouldn't be zinc anymore. It'd be gallium. So the number of protons identifies where the element is on the periodic table. And it is called the atomic number. So the number of protons identifies where it is on the periodic table, and it's specifically called the atomic number. So, let's say, for example, I know its atomic number is 10. So I go over to the periodic table. What element, bless you, is number 10? Neon, right? So if I have 10 protons, that can only be neon. There's no other element that has 10 protons. What if I had atomic number 20 with 20 protons? Calcium, right? So the atomic number tells me the number of protons, tells me the name of the element. The atomic number is also given the symbol big Z. So they're going to be used interchangeably. So atomic number means number of protons, means big letter Z. Those are all used interchangeably. How many people have heard all of this before? For the most part? Okay, good. All right, in that case, we'll move over to isotopes. So, all atoms of a similar element, right? All nitrogens always have 7 protons, and all irons always have 26 protons. All rubidiums always have 37 protons. But we can change the number of neutrons and not change the element. So an element's defined by its number of protons, but I can mess around with its neutrons and electrons. That's okay. I just can't change the number of protons. This means that I can have one sample of element with 2 different masses. So, for example, magnesium. What is its atomic number if you can see it from where you're sitting? 12. So how many protons does it have? Okay. Magnesium always has 12 protons. But can have 12 or 13 or 14 neutrons. Those are all possible combinations. So atoms with same number of protons but different number of neutrons are called isotopes. So they're all magnesium, but they're in a family called isotopes. So I have 3 isotopes of magnesium. And there's a way of figuring out the relative amounts of all these, because there's always going to be one isotope that's more prevalent than all the others. In this case, magnesium typically is 12, but it could be 13 or 14, but most of the time it's 12. So how do we use this knowledge of isotopes, protons, neutrons, and electrons to figure out these masses on the periodic table? We look at the atomic number, which is the number of protons, the mass number, which on this particular periodic table is surprisingly small. They put very small numbers. So oxygen is 16, its mass is 16, and its number of protons is 8. So, right, mass number is now considered A, atomic number is Z, the symbol for generic sake is X. So I could have a few different combinations of isotopes, and we can write out the different symbols for each. Before we do that, let's talk about this mass number. So, right, we have protons, electrons, and neutrons. Do electrons count when I figure out the mass? No, right, because they're so tiny. So the mass is just the number of protons and the number of neutrons. So A is protons plus neutrons, where Z is just the number of protons. How does number of electrons figure into this? Not at all. Not at all in this case. So while it's useful to know the number of electrons, it doesn't affect knowing the mass or the atomic number. So let's say I have my magnesium, again, that had 12 protons and 12 neutrons. Does everyone understand that very tricky P means protons, N means neutrons? Okay, I just don't feel like spelling them out over and over again. First question, let's say magnesium is neutral. How many electrons should it have? 12 also. And because I'm lazy, that's how I write electron. E minus. All right, so then let's figure out what is magnesium's atomic number. 12, good. So I'd say 12 Mg. What is magnesium, in this case, mass number? 24. No one had to use their calculator. Very impressive. Is it too cold in here? Let's see if I can. There's only 3 settings in here. Cold, neutral, warm. So I'll move over to warm. That may make a difference. All right, what if we have one of the other isotopes? Let's say I have this isotope of magnesium with 12 protons, 13 neutrons. How many electrons does this version have? Still 12. Just checking. Okay. What would this isotope's atomic number be? Mass number is 25. Atomic number is 12. All right, so if you're looking at the periodic table, it's still all the same. Well, if I have my third isotope, how many electrons does my third isotope have? Still 12. Good. Okay, so then what is the mass of this magnesium? 26. All right, let's do a thought experiment. Let's head over to our periodic table. On our official periodic table, the mass is 24.3. So which of these 3 isotopes, I'll number them, which of these isotopes, number 1, number 2, number 3, is the most predominant isotope if its mass is 24.3 on average? The first one, right? Because it has a mass of 24. Right, so that's true. Like 80% of all magnesiums have a mass of 24. The other 20 is split between the other 2 isotopes. Good. How I feel so far? Confident? Good warm-up? Anything new? Anyone learned anything new today? Okay, we'll get to something new. Okay, let's look at some isotope practice problems. Let's say I have carbon-14. Which number tells me the number of protons, the 14 or the 6? 6. So how many protons does it have? Okay. How do I figure out the number of neutrons? Okay, 14 minus 6. So how many neutrons does that guy have? 8. 8, okay. And then how many electrons does this guy have to have? 6 also. Good. All right, so then let's look at how are these two related? What would I call those two guys related? They're isotopes, right? These guys are isotopes to each other. How do I know they're isotopes? Two ways, right? It's the same symbol. They're both C. Or they have the same number of protons. Their atomic number is the same. So if they're isotopes, they must have the same number of protons and electrons. But how many neutrons does this guy have? 5. Just 5. Good? All right. Let's talk then about what happens if I mess around with the number of electrons. So isotopes is what happens when I mess around with the number of neutrons. If I mess around with the number of electrons, I get something called an ion. Can I change the number of protons? No. Under no circumstances should you change the number of protons until we get to nuclear chemistry, the end of 109. But from here until May, don't mess around with the protons. You're not ready for it yet. You'll get ready, but you're not ready yet. So, this is just a definition from last week, right? Molecules are two or more atoms in a definite arrangement held together by some chemical force, typically a bond of some sort. All right, so here are just some regular molecules: hydrogen, water, ammonia, methane. Boring molecules. But we can change the number of electrons to make the atom no longer neutral. So an atom, or an ion, is an atom, group of atoms, so an atom or a molecule that has a net charge, right? So a group of atoms stuck together would be a molecule. It's going to have a net charge due to a loss or gain of electrons. So do I have it on this side? I do. So if I have a neutral molecule and I lose an electron, what will be the overall charge of the molecule? If I had 6 electrons, 6 protons, and now I go 6 protons, 5 electrons, it's going to be positive, right? So a lost electron makes a positive molecule, or atom. Because there's only 2 options here. This one should be the negative one, right? So if I gain an electron, I now have a negative molecule. So these positive molecules and negative molecules have special names. Because what would it be if they were just called positive and negative? We call them cations and anions. So this is where I tell my favorite story every year. When I was in graduate school, I had a roommate my very first year, and a friend of ours found a litter of cats underneath their house. They were Siamese cats. The mom had either wandered off or died or some way. It was 4 little kittens. The person who owned the house kept one. They gave away another one. There's 2 cats left. My roommate and I agreed we were just going to take 1 cat between the 2 of us. But then we saw the cats, so we agreed we were each going to take a cat. So there was a boy cat that I had and a girl cat that she had. And they're Siamese brother, sister. And I was like, how cute would it be to have matchy-match names? Obviously, right? Boy, girl, Siamese. Since I had the boy cat, I thought I would name him Cation. And she had the girl cat. She could call hers Anne or Anion, right? Because that way they're positively and negatively charged. They stick together like Siamese twins. Boy, girl. I was thinking it's perfect. So I went ahead and named my cat Ion. She named hers Claudia. So my cat, positive feeling about that name. Anion, one negative feeling. So if that helps you remember it, feel good about my cat. Feel bad about what she should have named her cat. Claudia. Claudia's not even a good cat name, like a real human name, but definitely not a good cat name. All right, so then let's talk about how we figure out these cations that you should have positive feelings about versus the anions, negative feelings, bad news. Cat, my roommate, she and I still talk sometimes. Her cat is still alive. Mine passed away last year. So this is in memory of Cation. I just call him Ion for short, because Cation's kind of a long name. And Cat's kind of a stupid name, right? So if I had to go with one or the other, I called him Ion rather than Cat. All right, so let's talk about some examples. Let's say I have sodium. If I go to my periodic table, what is the atomic number of sodium? 11. So if it's the atomic number 11, how many protons does it have? Also 11. And if it's neutral, how many electrons should it have? Also 11. All right, so if I have sodium, there's normally 11 protons and 11 electrons. I could have a version of sodium called sodium with a plus symbol. What does the plus symbol tell me about what is the larger number, the protons or the electrons? Right? It means now I have more protons than electrons. Can I change the number of protons between this sodium and that sodium? No, can't do that. So it has to be still 11 protons. So what has happened to the number of electrons? It's gone down by how many? Right, it's gone down by 1. Good? So this would be a cation because it has a positive charge. Okay, what if I have another element? Let's do calcium. Okay, looking at calcium, its atomic number is 20. So how many protons does calcium bring to the party? 20. And if it's neutral, how many electrons would it also have? 20 as well. Okay, what if I now have this? I ran out of space. Jump below the gray line. Okay, I now have 20 protons and 18 electrons. So what element do I still have? Still calcium, I can't change that. But how do I tell the reader that it has lost 2 electrons? Plus 2. Good. All right, let's look at some negatively charged guys then. Let's think about, we'll do fluorine. All right, so fluorine typically brings to the party, I imagine all atoms hang out at parties and just like swap electrons or make bonds, or it is getting really warm in here. Is everybody warm? Too warm? Too warm? Let me switch it back down to neutral. Yeah, pretty much it's either cold, neutral, or hot. Those are our options in the building. All right, so if I have fluorine, 9 protons, 9 electrons. If I make F minus, how many protons does F minus have? Still 9 protons. But now how many electrons this must have? 10, right? 10 electrons. Okay. What if I have let's do sulfur. Let's do sulfur. Let's say sulfur has, its atomic number is 16. So how many protons does sulfur typically have? 16 protons. So then it must have 16 electrons. If I have a version of sulfur that is 16 protons and 18 electrons, how do I tell the reader that? What letter symbol do I give it? All right, so I still call it S, then -2. All right, the last thing we'll do today is we'll just do some practice ones. So how many protons and electrons are in this aluminum? How do I figure out the number of protons? Is it the 27 or the 13? Okay, it's 13. If it was neutral, how many electrons would it have? If it was neutral. If it was neutral, it would have 13, but I'm telling you it's plus 3. So how many electrons does it have? 10. Okay, what about is that selenium? Yeah, selenium. How many protons does this version of selenium have? 34. And if I tell you it's 2 minus, how many electrons does it have then? 36. Awesome. We will finish up chapter 2 on Friday. We'll do a group quiz. And next week we'll move into chapter 7, which is atomic theory. I'm putting all